Welcome to Exam 3, Problem 2. In this problem, we have a current I1 that's circulating counterclockwise, and it has a total current of 1 amp. And we have a current I2, a long current going straight, directed downward to the left, and it has a total current of 3.1415 amps. The radius of I1, radius R, is 1 meter. The question is, what is the total magnetic field at the center of the loop? Now, if we think about this, the magnetic field due to I1, by the right-hand rule, if you wrap your fingers around the loop with your thumb going the direction of I1, the magnetic field loops up and over and under and comes out through the middle, right? So the magnetic field for I1 is pointing up out of the page. If you wrap your fingers around I2 and point your thumb in the direction of I2, then the magnetic field here goes up and over and down on that side. So the magnetic field from I2 right over here is headed into the page, right? So magnetic field from I1 at the center of the loop is headed out of the page. The magnetic field from I2 at the center of the loop is headed into the page. So what then are the magnetic fields? Well, if we pop over to the equation sheet, right, for I1 we're talking about a magnetic field at the center of a current loop of radius R. All right, so for I1, talking about B is mu naught I over 2 pi R. All right, so mu naught is 4 pi times 10 to the minus 7th. Where's mu naught? 4 pi times 10 to the minus 7th Tesla meters per amp, right? All right. Four pi times 10 to the minus 7 Tesla meters per amp. Put a space there to fix that problem. Okay, and then I is 1.1234 amps, and then 2 R. R is 1 meter, so that's 2 meters. All right. So the amps cancel out, the meters cancel out. We're left with Tesla, and this is coming up out of the page, so we're going to leave it as positive, right? Okay, 4 pi times 10 to the minus 7th times half. So 2 pi times 10 to the minus 7th. Oh, from last time. Let's go over here. Mu naught. I'm going to go ahead and put in mu naught because we'll be using it probably more than once. So we're looking for 1/2 times mu naught, basically, is what this comes down to. Is that correct? 1/2 times mu naught. All right, so 6.283 times 10 to the minus 7th Tesla. We'll go 6.2832 times 10 to the minus 7th Tesla. 6.2832. My memory is gone. 6.2832 times 10 to the minus 7th Tesla, coming up out of the page due to I1. So let me put a 1 there, all right, and put a 1 there. So we're pretty clear. So we're clear that that's due to I1. Now, the the magnetic field to I2 is headed into the page at this point. And what is the magnetic field due to I2? Well, the magnetic field from a long current in a long straight wire is given by this equation, mu naught I over 2 pi R. All right, mu naught I over 2 pi R. So let's come back over here. All right, B2, then I2, right? So it's very similar to The last equation, 4 pi times 10 to the minus 7th Tesla meters per amp. Let's do amps. And 3.1415 amps, right? And we're going to be dividing by 2 pi r, which comes to just 2 pi meters, right? And up front, I'm going to stick a minus sign because we know this is headed into the page, right? Okay, so for this one, it is mu naught times 3.1415 amps divided by 2 divided by pi is 3.283, right? Negative 6.283 is 10 to the minus 7 Tesla. And in fact, the total field then is the sum of these. And that is essentially 0 Tesla, right? 0 Tesla. We could put that 0.0002 out there if we wanted, but that's really simply because I put the current at 3.1415 instead of making the current pi. So 0 Tesla is the total magnetic field at the center of that loop. And that's it for problem 2.